Hello everyone, my name is Orazio Toscano. I am from Ericsson, in particular from the Italian side of Genoa, and today I really appreciate this opportunity to present this article entitled Leveraging the 5G Architecture to Mitigate Amplification Attacks, prepared together with the friends of CNR, the National Research Council, CNIT, the National Inter-University Consortium for Telecommunications, Infocom, an excellent technological SME, and the famous Polytechnical University of Turin, all precious partners belonging, among many others, to the Astrid cybersecurity project, to whose activities this speech is dedicated, and that received funding from the Horizon 2020 EU Research and Innovation Programme. So, here is the outline of the presentation. I will start with a brief introduction about our approach. Then I will give an overview about the Astrid framework. After that, I will introduce Astrid in the 5G context, describing packet inspection in the 5G core. I will then present some use cases with particular focus for the distributed denial of service NTP amplification case. After that, I will describe the Analytic toolkit as core detection tool of the Astrid framework and present the tool evaluations. Finally, I will sketch the activity conclusions and give you some insights about our future work. We all know how dangerous are the distributed denial of service attacks for their ability to impair also large organizations. These kind of attacks are still considered among the most dangerous, particularly for network and service providers, as they can paralyze large parts of their customer networks. A very effective denial of service attack case, or better subfamily of cases, are the infamous amplification cases that exploit hundreds or thousands of buggy or misconfigured servers on the internet. As we can see in this picture, the attack starts from a botnet of compromised nodes which query a large number of servers while spoofing the IP address of the victim. Such servers send to the victim responses that are far larger in size than the original messages that triggered them, generating the amplification effect. There are many internet protocols where small queries may trigger larger responses, as we can see in this table, where the amplification factor, namely how many times the response is bigger than the original query, is shown. As we can see, it may range from a few to 1,000 times. Stopping these kind of attacks at their roots would be possible in theory by applying safe configuration to servers, blocking unnecessary ports, activating anti-spoofing filters, and so on and so forth. However, it would be difficult to achieve in practice because it depends on each organization that connects servers and devices to the internet. However, the new technologies, and in particular the 5G architecture, offers new opportunities to integrate monitoring and inspection functions at the edge, which can be used to detect and mitigate distributed denial of service attacks before their amplification. To this aim, a specific solution has been conceived and implemented, the so-called Analytic Toolkit, ATK, and integrated into a suitable innovative framework, Astrid, that I am going to describe in the following slides. The Astrid framework has been conceived to decouple detection and cybersecurity analytic services from the implementation of virtual services, the business logic. In this picture, we can see a simplified view of the Astrid architecture. In the Astrid framework, an external software orchestrator is used to deploy the virtual services, starting from descriptive templates. For example, in our work, we use the Kubernetes for this purpose. The only requirement for the service deployment process is to include Astrid agents within each virtual function. Several monitoring and inspection agents have been integrated in the architecture, including plain elastic beads, Logstash, and purpose-specific agents developed by the project, mostly consisting in inspection tools within the Polycube framework that run eBPF programs. A special kind of agent, named Local Control Plane (LCP), acts as a common control point to all other agents, including support for different configuration methods, REST APIs, command line, and so on. The framework also assumes that a management API is exposed by the service orchestrator. This interface is used to collect information about the current service topology and its configuration. In this case, we developed an Astrid adapter for retrieving all the necessary information which is not provided by the plain Kubernetes management API. The architecture builds on and extends the well-known and proven Elastic Stack by collecting events and measurements on a Kafka bus and delivering them for real-time processing, the ATK in our work, and internal storage, Elasticsearch. Events generated by the ATK are again published on Kafka, but using a different topic, and consumed by the dashboard that is not shown in this picture since it is not relevant in this work, Elasticsearch, and the security controller. That is a rule management system based on rules that takes control and management actions based on internal policies associated to the specific detection service. The definition of policies follows an event condition action pattern, which triggers one or more actions when an event occurs, if some context conditions are satisfied. Finally, a context manager provides the abstraction of the whole system, including the description of the service topology and its configuration, the list of available agents and the network parameters of the LCP, parameters that can be changed for each agent, eBPF programs available, and so on and so forth. It exposes a common REST interface for changing the configuration of local agents deployed within each virtual service, independently of specific protocols and syntax. The Astrid framework allows a great flexibility in combining together different agents and analytic engines, following a programming model that supports both streaming and offline analysis. This allows the creation of a very effective custom processing pipeline, as the one for the ATK that we use in this work. Without diving too deeply into the innovative 5G architecture and its undoubted and innumerable benefits, which go beyond the topics that we are illustrating and the time allowed, and which would deserve a dedicated presentation, we need to briefly elaborate on the user plane and especially the user plane functions, UPF, which play a crucial role in our approach. In the 5G architecture, the user plane carries packet data units, PDUs, Ethernet, IPv4, IPv6, from the user equipment, UE, to an external data network, DN, and vice versa. A PDU session is created between the UE and the UPF, which encapsulates the PDUs and carries them through the access network, AN. Indeed, different tunnels are created on the air and wired interface, with the AN relaying packets in between. The UPF is therefore the outermost network function in the 5G network that processes IP packets generated from or intended to the UE. It is mostly conceived for packet steering to from multiple data networks, for anchoring in case of mobility, and for quality of service and traffic policies enforcement. Even if this is not explicitly considered by the 3GPP specification, not yet at least, the UPF appears a perfect point for traffic monitoring at the edge. As a matter of fact, UPF are software functions that can be easily replicated for scalability, and therefore they probably represent the best point in the 5G core and also the internet, where packets can be inspected with fine granularity. Among the broad set of internet servers that can be exploited for amplification, we selected the Network Time Protocol, NTP, because it has one of the largest amplification factors and a huge number of public servers. Indeed, NTP is among the top emerging network attack vectors. However, our approach can be applied by other protocols by simply changing the configuration of the monitoring agents. The NTP attack is based on sending a command called monlist to an NTP server. The server returns the addresses of up to the last 600 machines that it has interacted with. The requested packet is only 234 bytes long, but the response may sum up to several dozens of kilobytes, depending on the numbers of returned addresses. We monitor NTP packets in the UPF of the 5G core network, and we switch between two kinds of measurements, depending on the current context: a coarse-grained indication, the number of NTP packets seen, and a fine-grained indication, the number of NTP packets containing the monlist command. This second parameter is more suited for the purpose of detecting the amplification attack. However, it needs deep packet inspection, and that usually entails slower processing. In the next slide, I will describe how the ATK processes the two measures and switches between them at runtime, chasing an optimal balance between the overhead of the inspection and the accuracy of the detection. The Analytic toolkit, ATK, is the component responsible for analyzing quasi-real-time data, performing estimation based on historical time series, and finding anomalies. It is therefore a general-purpose tool which can be applied to a plurality of attacks. Its behavior can also be easily adapted to multiple use cases through the rich REST-based configuration API. The implementation of the ATK is compliant with the Astrid framework. Its internal architecture is shown in this figure and based on two microservices, the proxy and the engine. The proxy interfaces the internal logic with external components by reading writing from to the common message bus and by exposing the REST configuration API. Therefore, it implements a data adaptation function. The engine includes a battery of estimators, each one processing the data from a different node, which work under the control of the estimator manager that implements the main detection logic and forwards the data collected by the proxy to the estimator, which compute the forecast based on what they learned in the past, and the results are then returned to the estimator manager for changing the current status if the case, and performing a correlation between different nodes. Finally, both the current status and the correlation are pushed to the proxy and published on the Kafka bus. Each estimator is responsible to predict the value expected at time t by using all the previous historical values. Their implementation makes use of standard ARIMA, autoregressive integrated moving average, provided by Python stats model library. The larger is the historical base, the more daily, weekly, and seasonal patterns that can be captured by the estimators. The behavior of the ATK is governed by the state machine shown in this part of the picture. The three states reflect the normal state, business as usual, BAU, suspicious, warn, and attack configuration, alarm. The state machine is then re-evaluated at every step by comparing the current measurements with the estimations. The ATK persists in the normal state as long as the difference between the current measurements and the estimation is under a proper threshold. Otherwise, it switches to the warning status. During operation, the new measurements are continuously added to the time series to continue training. However, real values are replaced by their estimations when the status is not business as usual to prevent overfitting. In the warning status, the fine grain measurements are also collected to improve the accuracy of the detection. These values are compared with different thresholds that account for individual deviation or correlated variation in terms of area, kind of nodes, and so on and so forth. The ATK switches and remain in the alarm status when either one node exceeds the individual threshold or a number of nodes exceed the correlation thresholds. In both cases, this should happen for a number h of consecutive evaluations, applying a proper hysteresis to avoid false positives. We set up an experimental testbed to carry out functional and performance validation. For packet inspection, we used the Dynamo Agent 11, a service of the Polycube framework, which provides a common control plane for running different eBPF programs and collecting their measurements. We also developed the policies for the security controller. They are used to push two different eBPF programs to Dynamon. One collects coarse-grained measurements, and the other one also includes fine-grained measurements, as described. The testbed implements the scenario depicted in the use case with 9 UPF connected to the same data network, and these nodes are grouped into 3 not overlapping areas. The ATK was trained offline with a wave profile, which is representative of typical daily variation. At this stage, we only focus on the ATK and on the Astrid framework, so we didn't deploy a working 5G network, but replaced the user equipments with software traffic generators, TG. Each traffic generator creates NTP packets according to different traffic profiles, and a subset of 3 traffic generators emulated a small botnet that generate monlist packets. They can be placed in the same or different areas. Here we show the measurements reported to the ATK and how its internal state evolve during the simulation. Even if the attack was quite limited in size, the number of queries was below those generating during normal peak periods. The ATK correctly generated a warning only when the anomaly occurred. Beyond the operation of the ATK engine itself, some delay can be introduced by the ACID framework while changing the configuration of the network agents, and we therefore investigated in detail the composition of these delays by splitting them into 2 components: processing introduced by the context manager and the configuration of the local agent, Polycube. And this table shows that the delay is very limited, around a couple of seconds, that have a very marginal impact on the timescale of the ATK. Summarizing, in this paper, we have proposed a concrete application of the Astrid framework to detect amplification attacks in virtualized 5G networks. Our approach does not require any modification to the 5G architecture and protocols, but only need the addition of simple agents. Preliminary performance analysis show that the small delays are very limited and that they have a very negligible impact on the specific detection process. By combining volumetric measurement with deep packet inspection, we can easily monitor large distributed infrastructures and scale well with the number of users and access networks. Future work will investigate more in detail the effectiveness and accuracy of the detection with different traffic profiles and attack patterns, also include more refined correlation schemes. And that's all from me. Thank you very much for your attention.